Here's a question that should keep you up at night. How would you know if you were inside a black hole right now? What test could you perform? What observation could you make that would tell you whether you're in normal space or trapped inside an event horizon? Think about it for a second. Really think. Because the answer is going to disturb you. You can't know. There's no local measurement you can make that would tell the difference. If the black hole is big enough, and I mean really cosmically big, the curvature of space inside would be so gentle that you'd never notice it. You'd see stars, galaxies, a perfectly normal universe. Everything would look fine. Everything would feel fine. The laws of physics would work exactly as expected. And yet, you'd be doomed. Not in some metaphorical sense, actually doomed. Because inside a black hole, all paths lead to the singularity. You can't escape. You can't even stay still. The geometry of space-time itself is dragging you unavoidably, inexorably toward total destruction. Now here's the kicker. Some very serious cosmologists think we might actually be inside a black hole. Not as a joke, not as a thought experiment, as a genuine possibility consistent with everything we observe about our universe. And if they're right, the implications are absolutely staggering. What a black hole actually is and why it matters. Before I can explain why we might be inside a black hole, I need to make sure you actually understand what a black hole is. Because most people, even smart people, even people who've read pop science books, have a completely wrong picture in their heads. The popular image is this. A black hole is a thing, an object, a dark, menacing sphere floating in space, sucking everything toward it like a cosmic vacuum cleaner. Get too close, you get sucked in. Stay far away, you're fine. That picture is wrong in almost every important way. A black hole is not a thing. It's not an object. It's a region of space-time with such extreme curvature that the geometry itself goes haywire. The surface of a black hole, what we call the event horizon, is not a physical barrier. There's nothing there. No membrane, no wall, no material substance. It's just a mathematical surface, marking the boundary of a region from which escape is impossible. Let me say that again because it's crucial. The event horizon is not a place where something stops you from leaving. It's the boundary beyond which all future paths point inward. There's no force holding you in. The space-time geometry itself has twisted into a shape where outward simply doesn't exist as a direction you can travel. Imagine you're an ant walking on a surface. Normally, you can walk in any direction you want. North, south, east, west. But now imagine the surface is curved in such an extreme way that all directions, every single direction you could possibly walk, lead to the same place. A hole in the center. That's what happens inside a black hole. All time-like paths lead to the singularity. Not because you're being pulled, because the geometry doesn't offer any other option. This is so counterintuitive that it hurts most people's brains. How can there be no way out if there's no barrier? How can you be unable to escape if there's nothing stopping you? The answer is, you're thinking about space when you should be thinking about space-time. In general relativity, space and time are mixed together. And inside an event horizon, the character of the coordinates changes. The time-like direction, the direction you're forced to move through just by existing points toward the singularity. Moving toward the singularity isn't a choice. It's as inevitable as moving forward in time. Let me put it this way. Right now you're moving through time, 1 second per second, relentlessly, in one direction. Can you stop? Can you go backwards in time? No, you're stuck on a one-way trip into the future. Well, inside a black hole, you're stuck on a one-way trip to the singularity for exactly the same reason. It's not about forces, it's about the structure of space-time. Now, here's where things get weird. All of that, the event horizon, the inescapable path to the singularity, the twisted geometry, only happens if you're inside the Schwarzschild radius. That's the critical size where the gravitational field is so strong that the escape velocity equals the speed of light. For an object of mass m, the Schwarzschild radius is r equals 2gm divided by c squared. G is Newton's gravitational constant. C is the speed of light. Plug in the mass of the sun, and you get a Schwarzschild radius of about 3 kilometers. If you could compress the sun down to a sphere with radius less than 3 kilometers, it would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. Compress the entire Earth down to the size of a marble, and it'd be a black hole. For a human being, the Schwarzschild radius is about 10 to the minus 25 meters, 100 billion times smaller than a proton. You're not in any danger of becoming a black hole. But here's the thing. The Schwarzschild radius scales linearly with mass. Double the mass, double the radius. And for very large masses, the Schwarzschild radius can be huge. Consider a supermassive black hole at the center of a galaxy, say, 1 billion solar masses. The Schwarzschild radius is about 3 billion kilometers. That's roughly 20 times the distance from the sun to Earth. A sphere that big, and everything inside it is trapped forever. Now scale up more. 1 trillion solar masses, Schwarzschild radius of 3 trillion kilometers, or about 0.3 light years. A quadrillion solar masses, 300 light years. A quintillion, 30,000 light years. You see where I'm going with this. The Schwarzschild radius can be arbitrarily large if you have enough mass. And the universe contains a lot of mass. The observable universe contains roughly 10 to the 53 kilograms of matter and energy. What's the Schwarzschild radius for that much mass? About 13.7 billion light years, which is astonishingly almost exactly the size of the observable universe. Now, does that mean the universe is a black hole? Not necessarily. The calculation I just did is oversimplified. It assumes all the mass is concentrated in one place, which it's not. The universe is roughly homogeneous on large scales, not a single collapsed object. But the fact that the numbers are even close is suggestive. And it raises a question that cosmologists have been asking very quietly for decades. What if the Big Bang, the apparent beginning of the universe, the moment of infinite density and temperature, is actually the singularity at the center of a black hole? And what if we're living in the interior, watching space-time expand away from that singularity, not realizing that we're trapped inside an event horizon that encompasses the entire observable cosmos? That's not a fringe idea anymore. That's a serious proposal, with actual mathematics behind it, published in peer-reviewed journals. And I'm going to explain to you why it might be true. But first, you need to understand something that almost nobody tells you about black holes. They're not static. They have dynamics. They evolve. And the interior of a black hole is not what you think it is. The interior of a black hole is a moment in time. Most people imagine the inside of a black hole as a sort of dark, empty region of space where you're falling toward a central point. But that's not right. The inside of a black hole is more like a moment in time than a place in space. Let me explain that, because it's genuinely bizarre. When you cross the event horizon of a black hole, something strange happens to the structure of space-time. Outside the horizon, the radial direction, the direction toward or away from the center, is space-like. That means you can move in either direction. You can move toward the black hole or away from it. It's a choice. Inside the horizon, the radial direction becomes time-like. That means moving toward the singularity is no longer a spatial choice. It's a temporal inevitability. The singularity is not a place at the center of the black hole. It's a moment in your future, an event that will happen to you no matter what you do, just like tomorrow will happen to you no matter what you do. This is why you can't escape from inside a black hole. It's not that you're not fast enough. It's not that the gravity is too strong. It's that escaping would require moving backward in time, which is impossible. Now here's where this gets relevant to the universe. If the universe is the interior of a black hole, then the Big Bang singularity isn't a moment in the distant past at a particular location. It's a moment in time that occurred everywhere simultaneously. And the expansion of the universe, the fact that galaxies are moving away from each other, that space itself is stretching, that's not an explosion from a point. It's the inevitable evolution of space-time away from a past singularity. Think about it this way. Inside a black hole, all paths lead to the singularity in the future. But what if you're in a black hole where all paths come from a singularity in the past? That's essentially what the Big Bang cosmology describes, a past singularity from which everything emerged. And here's the kicker. Mathematically, the two scenarios are related. If you solve Einstein's equations for the interior of a black hole, you get a space-time that expands from a past singularity and eventually contracts to a future singularity. Sound familiar? It should, because that's also the solution for a closed, finite universe in standard cosmology. The Feynman equations, the equations that describe the expansion of the universe, are the same damn equations that describe the interior of a black hole, just written in different coordinates. Let me be very clear about what I'm saying. The mathematics that describes a homogeneous, isotropic, expanding universe is identical to the mathematics that describes the interior of a black hole. They're the same geometry, viewed from different perspectives. So why do we call one a universe and the other a black hole interior? Mostly convention and perspective. If you're outside the black hole, you see an event horizon and you call it a black hole. If you're inside, you see an expanding space full of matter and energy and you call it a universe. Now, you might say, okay, but we're not inside a black hole because we don't see an event horizon. We look around and space looks infinite, or at least very large. We're not trapped in some small region, right? But that's only a problem if the black hole is small. If the black hole is absolutely enormous, if the Schwarzschild radius is comparable to or larger than the size of the observable universe, then you wouldn't see the horizon. You'd be so far from the horizon in the deep interior that the curvature would be negligible on observable scales. Think about the Earth. The Earth's surface is curved. But if you're standing in a field, it looks flat. You have to go far enough, climb a mountain, fly in an airplane, go to space to see the curvature directly. The same applies to a black hole. If it's big enough, the curvature is gentle and you don't notice it locally. So the question becomes, is there any evidence that we're inside such a structure? Any signature we could look for? And the answer is, maybe. There are a few tantalizing hints. First, the cosmological horizon. In standard cosmology, we can't see beyond a certain distance because light from farther regions hasn't had time to reach us yet. That's the cosmic horizon. But here's the thing. Inside a black hole, there's also a horizon, the event horizon beyond which we can't see because no light can escape from outside to reach us. Are these the same thing? Could the cosmic horizon we observe be, in fact, an event horizon viewed from the inside? Some cosmologists think yes. Second, the entropy. Black holes have entropy. In fact, they have the maximum entropy possible for any object of a given size. The entropy is proportional to the area of the event horizon. This is the famous Bekenstein-Hawking entropy formula, S equals A divided by 4G, where A is the area of the horizon. Now, there's a weird coincidence. The observable universe also has an entropy, and that entropy is dominated by the entropy of the cosmic horizon. And the formula for the entropy of the cosmic horizon in cosmology looks suspiciously similar to the Bekenstein-Hawking formula for a black hole, almost like the universe is a black hole that's maximizing its entropy. Third, the expansion rate. Inside a black hole, space-time doesn't just sit still, it has dynamics. In a simple Schwarzschild black hole, the interior expands away from the past horizon and contracts toward the future singularity. In a more complicated rotating or charged black hole, the dynamics are richer. But the point is, expansion is expected inside a black hole. And we observe expansion. The Hubble expansion, dark energy, all of it could be reinterpreted as the natural dynamics of a black hole interior, not as some mysterious property of dark energy that we don't understand. Now, I'm not saying this is what's happening. I'm saying it's a possibility. A genuine, mathematically consistent possibility that fits the data we have. And it's not some crackpot idea. Lee Smolin, Nikodem Poplawski, and others have written serious papers exploring this. It's speculative, yes, but it's not fringe. And if it's true, if we are inside a black hole, the implications are staggering, because it means the universe we see is not the whole story. There's an outside, a larger universe that our black hole is embedded in. And that larger universe might contain other black holes, each containing their own internal universes. An infinite nesting of cosmologies, each one born from the collapse of matter in the universe above it. That's the multiverse, but not the kind people usually talk about. Not parallel universes from quantum branching, not bubble universes from eternal inflation. But a hierarchical structure of black hole interiors, each one a self-contained cosmos, causally disconnected from the others. It's one of the wildest ideas in cosmology. And it might be true. How would we know? We might not. Now let's talk about what would actually happen if we are inside a black hole. Because this is where people's intuitions completely fail and where the physics gets truly disturbing. If the universe is a black hole interior, then the Big Bang singularity is in our past, and there's another singularity in our future. That future singularity is the crunch, the moment when all of space-time collapses to infinite density and curvature, and everything ends. In a simple black hole solution, the Schwarzschild solution, this future singularity is inevitable. Once you're inside the event horizon, you will hit the singularity. There's no escape. It's as certain as death and taxes. Does that mean the universe will end in a big crunch? Maybe. But there's a complication. Our universe doesn't look like a simple Schwarzschild interior. We have dark energy. We have accelerating expansion. And that changes the dynamics. Dark energy, the mysterious stuff causing the expansion of the universe to accelerate, acts like a repulsive force. It pushes space apart. And if dark energy remains constant or increases over time, the universe will expand forever, getting colder and emptier, approaching a final state called the heat death. But here's the twist. Dark energy might not be constant. It might change. It might decay, or flip sign, or do something else entirely. We don't know what dark energy is, so we can't predict its long-term behavior with any confidence. And if dark energy changes, all bets are off. The universe could stop expanding and start contracting. The future singularity could be back on the table. Now, in a black hole interior, there's another possibility. The singularity might not be a point. It might be a Cauchy horizon, a surface beyond which the deterministic laws of physics break down. Crossing a Cauchy horizon would be like leaving the domain of predictability and entering a region where literally anything could happen. The laws of physics, as we know them, would cease to apply. This happens in rotating black holes, Kerr black holes. Inside a Kerr black hole, you don't immediately hit a singularity. Instead, you encounter an inner horizon, and beyond that, space-time becomes wildly unstable. Some solutions suggest you could pass through the inner horizon and emerge into a new region of space-time, possibly even a new universe. If our universe is the interior of a rotating black hole, then there might be a Cauchy horizon somewhere in our future, and crossing it would be unimaginable, literally, because the physics beyond that horizon might not resemble anything we've ever encountered. But let's step back and ask a more immediate question. How would you test this? How would you gather evidence that we're inside a black hole? The challenge is that from the inside, a black hole looks like a perfectly normal universe. The local laws of physics are the same. Light travels in straight lines, locally. Apples fall from trees. Quantum mechanics works. There's no obvious black holeness that you can point to. But there are subtle signatures you might be able to detect. Let me tell you about a few. First, anisotropy in the cosmic microwave background. The CMB, the afterglow of the Big Bang, is remarkably uniform, but it's not perfectly uniform. There are tiny fluctuations, 1 part in 100,000, that represent the seeds of all the structure in the universe today. If the universe is a black hole interior, the CMB fluctuations might have a specific pattern related to the geometry of the black hole. For instance, if the black hole is rotating, a Kerr black hole, there might be a preferred direction in space, an axis of rotation, that would show up as a systematic anisotropy in the CMB. We've looked for this. There are some anomalies in the CMB data, things like the axis of evil, a mysterious alignment of large-scale fluctuations that some people think might be evidence of rotation or other exotic effects. But the data is noisy, and the anomalies aren't conclusive. Second, the topology of space. If we're inside a black hole, space might be finite and have a non-trivial topology. It might loop back on itself, like a torus or some other compact manifold. And if that's true, we might be able to detect it by looking for repeating patterns in the distribution of galaxies or in the CMB. This is the same cosmic hall of mirrors effect I mentioned in a previous talk. If space is finite and has a small enough size, you'd see multiple images of the same structures in different directions. People have searched for this. So far, nothing definitive. But if the black hole is very large, the repeats might be beyond our observable horizon, and we'd never see them. Third, the expansion history. The way the universe expands over time depends on its energy, content, and geometry. In standard cosmology, we measure the expansion history by looking at distant supernovae, the CMB, and other probes. And what we found is that the expansion is accelerating, which we attribute to dark energy. But in a black hole interior, the expansion dynamics are different. The expansion is driven by the black hole's mass and angular momentum, not by some mysterious dark energy. So if we could measure the expansion history precisely enough, we might be able to distinguish between universe with dark energy and black hole interior. The problem is, the two scenarios make very similar predictions for the expansion history, at least with current data. We'd need much more precise measurements to tell them apart. Fourth, quantum gravity effects. If we're inside a black hole, and if quantum gravity becomes important at the singularity, there might be relics of quantum gravitational processes in the early universe. Things like primordial gravitational waves, non-Gaussianities in the CMB, or other signatures that don't fit the standard inflationary picture. We're starting to probe these effects with current and future experiments. The Planck satellite, the Simons Observatory, CMB, S4, these are all looking for subtle quantum gravity signatures. If we find something that doesn't fit the standard model, it might be a hint that the universe has a more exotic origin. But here's the frustrating part. Even if we find all these signatures, even if every piece of evidence points toward the black hole hypothesis, we can't prove it. Because we're inside, we can't see the event horizon from the outside. We can't compare our universe to other universes. We're stuck with indirect evidence, and indirect evidence is always ambiguous. That's the nature of cosmology. We get one universe to study, and we have to figure out its global structure from local measurements. It's like being an ant on a balloon, trying to figure out if the balloon is a sphere, a torus, or an infinite plane, using only measurements you can make on the surface. It's possible, but it's hard. And if the black hole is big enough, if the curvature is gentle enough, it might be impossible to tell. We might be inside a black hole, and we might never know for sure. The multiverse is a fractal of black hole interiors. Let me tell you about one of the strangest implications of the black hole universe idea. It's something that almost nobody talks about, but it's deeply, philosophically disturbing. If we're inside a black hole, then our entire universe, everything we see, everything that exists, all the stars and galaxies and planets and people, is part of a structure that formed from the collapse of matter in some parent universe. Somewhere out there, in that parent universe, there's a region of space that collapsed under its own gravity, crossed the Schwarzschild radius, and formed an event horizon, and we're inside that region. We're the interior. Now here's the disturbing part. From the perspective of the parent universe, that collapse happened very quickly. Once the matter crosses the event horizon, it rushes toward the singularity. The entire process, from horizon crossing to singularity, takes a finite amount of time, the infall time, which depends on the mass of the black hole, but it's always finite. For a solar mass black hole, the infall time is about 10 microseconds. For a supermassive black hole, it might be hours or days. For a cosmological scale black hole with the mass of the observable universe, the infall time is roughly the age of the universe, about 13.8 billion years. Do you see the problem? From the inside our perspective, the universe has existed for 13.8 billion years and will presumably continue to exist for trillions more. But from the outside, the perspective of the parent universe, the entire history of our universe, from Big Bang to heat death or Big Crunch, happens in the blink of an eye. A few seconds, or hours, or years at most. Our entire existence is the interior of a collapsing object in another universe, a brief moment in their time. And when the collapse is complete, when our universe hits the singularity, we're done, finished, gone. Now, you might say, but we don't feel like we're collapsing. We see expansion, not contraction. The universe is getting bigger, not smaller. That's true from the inside, but it's an illusion of perspective. Inside a black hole, the coordinates are such that space appears to expand away from the past singularity, but that's just a description of the geometry. From the outside, the whole thing is collapsing inward toward the future singularity. It's like falling into a black hole yourself. From your perspective, you don't feel any different. You look around, and space looks normal. But from the perspective of someone watching you from outside, you're frozen at the event horizon, red-shifted to infinity, disappearing into darkness. Different perspectives, same geometry, and in general relativity, all perspectives are equally valid. So, is our universe collapsing or expanding? Yes, both, depending on whose perspective you take. Now, here's another disturbing implication. If black holes contain universes, and if those universes contain black holes, which contain their own universes, then reality is a fractal, an infinite nesting of cosmologies, each one birthed from the collapse of matter in the layer above. Lee Smolin calls this cosmological natural selection. The idea is that universes which produce lots of black holes will spawn lots of child universes. And if the laws of physics in the child universes are similar to the parent, then over many generations, the multiverse will be dominated by universes whose physics is optimized for black hole production. Does our universe produce lots of black holes? Yes. Every massive star that goes supernova leaves behind either a neutron star or a black hole. There are probably hundreds of millions of stellar mass black holes in our galaxy alone, and billions or trillions in the observable universe. And that's just stellar mass black holes. There are also supermassive black holes at the centers of galaxies, intermediate mass black holes, and possibly primordial black holes formed in the early universe. Black holes everywhere. A fecund cosmos. If Smolin is right, then our universe is highly reproductive. It's spawning child universes at a prodigious rate, and each of those child universes might spawn their own children, and so on, indefinitely. It's a multiverse, but not the kind physicists usually talk about. It's not a branching tree of quantum possibilities. It's a genealogy, a family tree of universes, each descended from black holes in their parents, stretching back infinitely into the past and forward infinitely into the future. And we're somewhere in the middle of that tree, children of a black hole in some parent universe. Parents, in turn, to countless child universes growing inside the black holes in our own cosmos. Is this true? We don't know. We may never know. But it's a mathematically consistent picture, and it explains some puzzling features of our universe, like why the laws of physics seem fine-tuned for complexity and structure formation. If our universe is the product of cosmological natural selection, then the laws of physics have been evolved over countless generations to favor black hole production, which indirectly favors star formation, planet formation, chemistry, and possibly even life. We exist because the multiverse has been optimized for existence, not by design, by selection, by a sort of cosmic Darwinism playing out across a vast genealogy of universes. It's beautiful and terrifying and possibly true. Now, you might be wondering, if we're inside a black hole, what happens when we die? I mean, when the universe ends, when we hit the singularity or the heat death or whatever the final state is. Do we just stop? Is that it? In the standard picture, yes. The universe ends and there's nothing after. No continuation, no reincarnation, no afterlife for the cosmos. But in the black hole multiverse picture, there's a sense in which the universe lives on. Because even if our universe ends, the black holes within it continue to exist. And inside each of those black holes, a new universe is growing, expanding, evolving. Our descendants. So the end of our universe is not the end of the story. It's just one chapter closing while countless others are already being written inside the black holes we created. It's a kind of immortality. Not for us as individuals, but for the cosmos as a whole. A never-ending cycle of birth, evolution, death, and rebirth, playing out across an infinite hierarchy of black hole interior. And if that's true, then we're not just passive observers of the universe, we're participants in its reproduction. Every black hole we create, whether intentionally or just as a byproduct of stellar evolution, is a seed for a new universe. A new cosmos with its own stars, galaxies, planets, and possibly even its own intelligent life. We're not just studying the universe, we're making new ones. What happens at the singularity? Quantum gravity might save us. Now I want to address something that's probably been bothering you this whole time. If we're inside a black hole, and if the singularity is in our future, does that mean the universe is doomed? Are we inevitably headed toward a catastrophic end? The answer depends on what kind of black hole we're in, and on what quantum gravity does to singularities. In classical general relativity, Einstein's theory without quantum mechanics singularities are real, physical places where space-time curvature becomes infinite, and the laws of physics break down. If you hit a singularity, you're destroyed, crushed to zero volume, game over. But most physicists don't believe singularities are real. They believe singularities are a sign that general relativity is incomplete, that we need a quantum theory of gravity to describe what actually happens at those extreme conditions. Quantum gravity, whatever form it takes, whether it's string theory, loop quantum gravity, or something else, is expected to smooth out singularities. To replace the infinite curvature with something finite and manageable, the singularity isn't the point of destruction. It's a region where quantum effects dominate, and space-time might do something unexpected. What might it do? Several possibilities. One, the singularity might be a bounce. Instead of collapsing to infinite density, space-time might reach some maximum density and then bounce back, starting a new phase of expansion. This is the idea behind loop quantum cosmology, which replaces the Big Bang singularity with a big bounce, connecting our universe to a previous collapsing phase. If that's true for the future singularity as well, then hitting the singularity wouldn't end the universe. It would transform it, reboot it, start a new cycle. 2, the singularity might be a tunnel to another region of space-time. In some solutions to Einstein's equations, like the maximally extended Schwarzschild solution or the Kerr solution, the interior of a black hole connects to a white hole in another universe. You go in the black hole, you come out the white hole. This is almost certainly not physically realistic for real black holes, because the connection is unstable and would be destroyed by any small perturbation. But if quantum gravity stabilizes these wormhole-like connections, then the singularity might be a doorway, not a dead end. 3, the singularity might be a creation event. Instead of destroying information and structure, it might generate new information and structure, spawning new space-time regions with their own physics. This is speculative, obviously. We don't have a complete theory of quantum gravity, so we can't calculate what actually happens at the singularity. But the point is, the singularity is not necessarily the end. It might be a transition, a transformation, a beginning in disguise. And if we're inside a black hole, and if quantum gravity does something interesting at the singularity, then the ultimate fate of the universe might not be heat, death, or big crunch. It might be something far stranger. Now let's talk about something even more speculative, the possibility that we're not just in any black hole, but in a specially engineered one. Suppose an advanced civilization, and I mean really advanced, Kardashev Type 3 or beyond, gains complete control over space-time. They can manipulate gravity, create black holes at will, and possibly even control the interior properties of those black holes. Such a civilization might deliberately create black holes with specific properties. They might seed the black hole interior with matter and energy in a particular configuration, designed to produce a universe with specific features, stable atoms, star formation, planets, chemistry, maybe even life. In other words, they might create universes on purpose, and we might be living in one. This is the universe as a simulation idea, but with a twist. It's not a computer simulation. It's a physical universe grown inside a black hole in a parent universe that has very different physics from ours. The parent civilization might not even be biological. They might be post-physical entities, existing as pure information in some exotic substrate. They create black hole universes as a form of, art, experimentation, resource extraction. We can't know their motives. But the point is, it's possible. How would you test this? You'd look for signatures of fine-tuning. If the laws of physics in our universe seem suspiciously well-tuned for life or for some other purpose, that might be evidence that someone tuned them deliberately. And guess what? The laws of physics DO seem fine-tuned. The masses of fundamental particles, the strengths of the forces, the cosmological constant, all of these are in narrow ranges that allow for stable atoms, long-lived stars, and complex chemistry. Change any of them by a few percent, and you get a universe that's sterile, unable to support life. The standard explanation is the anthropic principle. We observe a fine-tuned universe because we couldn't exist in a non-fine-tuned one. It's selection bias. But another explanation is someone tuned it on purpose because they wanted to create a universe like ours. I'm not saying this is likely. I'm not even saying I believe it. I'm saying it's a hypothesis that fits the data and is not ruled out by any known physics. And if it's true, the implications are, I don't even have words for it. We'd be the product of deliberate creation by a higher level intelligence. Not in a religious sense, in a physical engineering sense. We're a project, an experiment, a work of art. And the really crazy part, if we're inside a black hole created by another civilization, then maybe WE could do the same thing. Create black holes with specific properties, seed them with matter, and watch new universes grow inside. We'd become gods, not metaphorically, literally. We'd be creating new realities, new cosmoses, new opportunities for life and complexity to emerge. Is this science fiction? Yes. But it's science fiction that's mathematically consistent with general relativity and thermodynamics. It's not magic. It's just very advanced engineering. And maybe, just maybe, that's what the universe is. An engineering project by a civilization so far beyond us that we can't even comprehend their existence. And maybe our descendants will do the same, creating universes within universes ad infinitum. It's a strange loop. We're created by those who came before, we create those who come after. An eternal cycle of cosmogenesis playing out across the hierarchy of black holes. Or maybe none of this is true, and we're just in a perfectly ordinary universe that happens to have some mathematical similarities to a black hole interior. We don't know. But the fact that we can even ask these questions, the fact that we can explore these possibilities with real mathematics and real physics is extraordinary. We're apes who learned to calculate the curvature of space-time, and now we're using that knowledge to wonder if we're inside a structure formed from the collapse of matter in some unimaginably larger reality. That's beautiful and terrifying, and exactly the kind of thing that makes physics worth doing. We're part of an eternal cycle. All right, let's bring this all together, because I've thrown a lot at you, and I want to make sure you understand what we're really talking about here. The question is, are we inside a black hole? And the answer is, we might be, and we might never know for sure. The mathematics of general relativity allows for it. The structure of a homogeneous, expanding universe is identical to the structure of a black hole interior. The Schwarzschild radius of the observable universe's mass is roughly the size of the observable universe. The cosmic horizon looks suspiciously like an event horizon viewed from the inside. All of these are suggestive, but they're not proof, because the equations are ambiguous. The same geometry can be interpreted as a universe or as a black hole interior, depending on your perspective and boundary conditions. And here's the deep philosophical point. It might not even be a meaningful question. Because are we inside a black hole presupposes that there's an objective, observer-independent answer. But in general relativity, reality is observer-dependent. Different observers slice space-time into space and time in different ways. What one observer calls expanding space, another might call collapsing matter. So maybe the question isn't, are we inside a black hole, but rather, is it useful to describe our universe as a black hole interior? And the answer to that is, sometimes, yes. It gives us new perspectives, new ways of thinking about the Big Bang, cosmic horizons, entropy, the multiverse. Whether it's true in some absolute sense might not even be a well-posed question. It might just be a choice of description. But that doesn't make it unimportant, because the black hole universe picture leads to testable predictions, signatures in the CMB, anomalies in the expansion rate, patterns in the topology of space. If we find those signatures, we'll have evidence that the black hole interpretation is not just a mathematical curiosity, but a physical reality. And if we don't find them, that doesn't prove we're not in a black hole. It just means the black hole is big enough, smooth enough, that the signatures are too subtle to detect with current technology. So we're left with uncertainty. And that's okay. That's the nature of cosmology. We're trying to understand the global structure of reality using local measurements, and there are inherent limits to what we can learn. But here's what we do know. We know that black holes are real. We've observed them, measured them, studied their properties. We know that general relativity describes space-time curvature with exquisite precision. We know that the mathematics of black hole interiors is virtually identical to the mathematics of cosmology. So the idea that our universe could be a black hole interior is not wild speculation. It's a natural extrapolation of known physics. And it's a reminder that the universe is stranger, more subtle, more deeply interconnected than we usually imagine. Let me tell you what I think is the most profound implication of all this. If we're inside a black hole, then the universe is not fundamental. It's emergent. It's a structure that formed from simpler ingredients in a parent universe. And that parent universe might itself be a black hole interior in a grandparent universe, and so on. There's no bottom, no ultimate foundation, just an infinite regress of black holes containing universes, containing black holes. That's a very different picture from the one most people carry around. Most people think of the universe as the universe, the only one, the fundamental level of reality. But if the black hole multiverse picture is right, there is no fundamental level. It's black holes all the way down and all the way up. Every level is as real as every other level. You're not more or less real because you're inside a black hole. You're just at a particular level in an infinite hierarchy. And beings at other levels, in the parent universe or in child universes inside black holes in our universe, are equally real, living out their lives in their own cosmoses, completely unaware of each other. It's a multiverse, but a very specific kind. Not the many worlds of quantum mechanics, not the bubble universes of eternal inflation, but a nested, hierarchical, causally connected web of universes, each born from the collapse of matter in the layer above, each giving birth to new universes in the black holes it contains. And if that's true, then the questions we ask about our universe, why these laws of physics, why this amount of matter, why does anything exist at all, might have answers that point to the parent universe. The laws of physics in our universe are what they are because of the conditions under which the black hole formed in the parent universe. We're not the result of some cosmic accident. We're the offspring of a specific physical process. And understanding that process, understanding how black holes give birth to universes, might be the key to understanding why our universe is the way it is. Now, I want to end with a thought that's more personal than scientific. When I first heard about the black hole universe idea, my reaction was, that's horrifying. If we're inside a black hole, we're trapped, doomed, headed inevitably toward a singularity. But the more I thought about it, the less horrifying it seemed. Because being inside a black hole doesn't change anything about your day-to-day life. You still experience time flowing forward. You still have choices, goals, relationships. The physics is the same. The stars shine. Life goes on. And in a sense, we're always doomed. Even in a perfectly ordinary universe, the heat death comes eventually. Entropy wins. Everything decays. On long enough time scales, nothing lasts. So the fact that we might be inside a black hole, headed toward a singularity in the distant future, doesn't make things worse. It just gives us a different story about the ultimate fate of the cosmos. And honestly, I find the black hole story more interesting because it connects us to something larger. We're not isolated. We're part of a vast hierarchy of nested universes, each one a black hole interior in the layer above. We're children of the cosmos in a very literal sense. And someday, billions of years from now, when the stars burn out and the black holes evaporate and the universe approaches its final state, there will still be black holes in our universe. And inside those black holes, new universes will be growing, expanding, evolving, new stars, new planets, new life. Our universe will end. But the story doesn't, because we're part of an eternal cycle of creation and destruction, playing out across an infinite hierarchy of realities. That's not doom, that's legacy. That's meaning in the face of an otherwise meaningless cosmos. So are we inside a black hole? Maybe. Probably not, but maybe. And if we are, I think that's beautiful, because it means we're not alone. We're part of something vastly larger than ourselves. A cosmic genealogy stretching infinitely into the past and future. We're black hole children, and someday we'll be black hole parents. And that, to me, is one of the most profound ideas I've ever encountered.